So for this learning module, we'll look at how to apply the concepts of rigid body equilibrium in two dimensions. Before we do that, I wanted to introduce the concept of at least a two-force member. I won't talk about the three-force member, even though it's in the title of this slide, because it's not particularly relevant in two dimensions. So we'll look at an example problem to really drive home what this means. And in addition, it will be relevant when we move on to the analysis of trusses in chapter 6. But key idea behind equilibrium, and I've been emphasizing this really since chapter 2, when we first drew free body diagrams, is that if an entire body is in equilibrium, then all of its components are in equilibrium as well. And if one of those components has only two forces acting upon it, then those forces naturally have to be in equal and opposite directions. And what that really does is reduce the number of unknowns in this system, which you might view as generally 4, the magnitude of the force at both points A and B, along with the directions, to 1. All that I really need to know in order to describe the equilibrium of the system is that single magnitude of the force, which is equal and opposite. So in terms of the steps for solving 2D equilibrium problems, if you don't have a coordinate system, it's good to set one up. Of course, you would want to choose the one that's most convenient for your problems. Oftentimes for textbook examples, that is the traditional XY coordinate system, with X being purely horizontal and Y vertical, but oftentimes choosing a local coordinate system that reflects the geometry of your situation can yield a simpler solution. Draw the free body diagram. The majority of these problems are interested in solving reaction forces, so that's really just a matter of taking the body and separating it from its supports and replacing the forces that are applied by the support structures at the point of application of the reactions, using those tables that we've talked about previously. And then in 2D, we have 3 equations of equilibrium. Equilibrium of the resultant force, meaning that the body doesn't translate horizontally or vertically, and our moment-based equation, which can be computed about any point, which just basically says that the body is not only not translating, but it's also not rotating. So one key point that I wanted to emphasize again, since in a 2D situation we only have 3 equations, and mathematically through linear algebra we can only solve through 3 unknowns. However, there are scenarios in which a system of reactions would have more than 3 unknowns, and the body is still stable. That just because we can't uniquely resolve each unknown in a reaction doesn't mean that the body's not in equilibrium. It just means that our back of the envelope technique isn't working. So those situations we actually call statically indeterminate, or as they have bolded here, indeterminate situation. But the more formal thing you'll hear down the road is statically indeterminate. And that just means we need a more sophisticated analysis technique. Point 2, what they're trying to say is if you solve these by hand using like a substitution or an elimination technique, obviously there's a bit of an art. And in order for solving for your unknowns, there's going to be equations that make sense to solve first in order to substitute back. However, if you're using kind of a standardized linear algebra approach, it really doesn't matter, of course. In addition, oftentimes we will assume a certain direction of our reaction forces or couples. And if they turn out to be negative, that doesn't mean that the answer is wrong. It just means that the assumed direction was incorrect. So in terms of an example here that will kind of emphasize the approach, along with talk about the importance of 2 force members, assume you have a beam that's supporting this 4 kilonewton load applied at point B. We can see that absent of this boom connection from C to D, this thing could not be in equilibrium, because the reaction at A, it could successfully oppose the vertical translation associated with this load, but it couldn't counterbalance the rotation that this load is going to tend to induce about point A. So we need an additional support system. We're doing that through this boom, which is pinned to the beam at point C. And we want to find the reactions at A and C. Now, when you look at this, you might say, okay, I'm going to separate the beam from its support structures. I know I've done this enough that at point A, I should have an unknown horizontal reaction and an unknown vertical reaction. And at point C, since it's a pin 2, I should have an unknown horizontal and vertical reaction. However, if you do that, while that is valid, you would have a 2D system with 4 unknown reactions. And since you only have 4 equations of equilibrium, you would think that's statically indeterminate. However, we can actually take advantage of that concept of a 2-force member that we spoke of previously. Namely, since boom CD only has the 2 reactions applied to it at C and D, we do know that in terms of, so when you think about like a pin, having it described in terms of its X and Y component, another way you can look at that is it's described in terms of its magnitude and direction in polar form. So for a two-force member like C and D, because there's only two forces being applied here, we can view the direction as being known. It's just going to be equal and opposite for the boon, whatever is being applied at D, and the magnitude is being unknown. So where I'm saying a lot of words here, it will just be easier to look and see at the free body diagram here to the right. You notice for the pin, we've replaced it with an unknown horizontal and vertical reaction. And for the boon applied at point C, since this boon is a two-force member, we can replace the reaction there by a single force with a line of action along the boon itself. And then the way that they're getting this 45-degree angle, if you look at the geometry of the setup, if I were to compute what this angle is, I could take the inverse tangent of the opposite over adjacent side length, which is just 1-to-1, so that's a 45-degree angle. And how are we going to go about doing this? Well, clearly the horizontal and vertical equations are pretty simple here. The question is, where should we compute the moment about for our rotational equilibrium equation? So you clearly would want to do it. I mean, if you kind of go through like in your head how this works, you can only do it at points where you have the geometry to actually compute the moments. So just looking at what you have here, you hopefully can convince yourself pretty quickly that you can only do it at points A, C, and B. However, the easiest point to actually do it, and you could argue this either way, but I think it's point A, because if we compute the moment about point A, the reactions at point A won't contribute to that moment because they're applied directly at that point. So you can kind of view the position vector as being 0. And in addition, if we were to do that, we only need to consider the vertical component of the reaction force FCD, because its horizontal component will have a line of action that goes through A. So really, in terms of determining the rotation about A, there's only two things that contribute. There's the 4 kilonewton force that's applied at B. And if you kind of think about holding the rod at A and pushing down at B, that's going to be a clockwise direction. So that's why that is negative, and it's at a perpendicular distance of 3 meters. That's where the 3 is coming from. And the reason we're only computing the vertical component of FCD, which we can get by taking the sine of multiplying the magnitude by the sine, and notice that that vertical component will rotate in the counterclockwise direction, so it will be positive, is because, again, the horizontal component doesn't contribute to rotation. So you notice just from enforcing rotational equilibrium by computing a moment about A, you can find this magnitude FCD. And once you have that, if you are solving it manually, you can substitute back in and get the remaining quantities that you don't know, namely AX and AY. So in this case, we'll notice that AX turned out to be negative. What that means is that that pin isn't serving to push the beam out of the wall, but rather it's pulling it back into the wall. When you look at the nature of these forces, that's probably not overly surprising to you. But again, the key point to realize is the X component being negative doesn't mean that these computations are wrong. It just means that the assumed direction is wrong. Same idea behind the Y component being negative as well. So that may be a little bit counterintuitive to you since the applied load is in the vertical direction, but what's happening is in order to have rotational equilibrium about point A, the magnitude of the force being applied by the boom has to be so large that the pin actually has to help pull it back down. So not overly surprising in this type of situation because that force is applied so far away from the support point at A. So hopefully this was helpful. I'm going to get the document out and work a few questions on the example quiz, or I should say the practice exam. I'll get it out that I think you should focus on for the real exam, and then we'll move on to the last 3 chapters. And it's going to be quick, but we're going to be able to get it all done and at least get you positioned well enough to be ready to move on to dynamics successfully.